In the last video we looked at the ratio of sides of a right angled triangle. If this right angled triangle contains angle A, then the side opposite angle A is this side here. I'm calling it little m. The side adjacent to A is little n, and the hypotenuse is little h. The sine of A was defined to be m over h. Here it is. Now, we saw from the simulation that it doesn't matter what size right angled triangle we have, the sine of angle A is unaffected. As long as these angles are the same, it doesn't matter how big or small the triangle is. So if we take this bigger triangle, the same angle A, the sine of it is opposite over hypotenuse. I'm calling this side here, the bigger triangle, big M, and the hypotenuse, big H. So we're going to prove that these two ratios are the same. Similarly for tan of A is opposite over adjacent. In the small triangle it's little m over little n. In the big triangle it's big M over big N. And finally we have the cos of A, that's adjacent over hypotenuse. So in the small triangle that's little n over little h. In the big triangle that's big N over big H. Proof. Well, the triangles are similar triangles. Why is that? Well, by construction these angles are the same. Also the right angles are the same. We're talking about right angled triangles. So two of the angles are the same in both triangles. So that means that the third angle is the same. Because how do we get the third angle? Well, we just add these two angles together and take the result from 180 to get this angle. If we do the same in this triangle, we're going to get the same result. So the third angle has to be the same. So if two angles are the same in two triangles, then the triangles are similar or equiangular. Now, we proved in an earlier video that if two triangles are similar, the corresponding sides are in the same ratio. So, let's get a pair of corresponding sides. Let's get the sides opposite angle A. Well, in the small triangle, that's small m. In the big triangle, it's big M. So these two sides are corresponding sides. So let's take the ratio of these two sides. We could put little m over big M or big M over little m, it doesn't matter. I'll put little m on top. Let's take another pair of corresponding sides. Let's take the sides opposite the 90-degree angle. These are corresponding sides. Let's take the ratio of these sides. Well, for the numerator we have to take the side from the small triangle first. So we have to take little h and divide by big H, because for this first ratio we had little m over big M. Finally, let's look at the remaining pair of corresponding sides. The sides opposite the angle up here. So we're talking about little n over big N. So we proved this in an earlier video. Now we could call these ratios S. I'll give them a name. They're all the same. S in this case will be a number less than 1, because little m is less than big M. So the numerators of these fractions are less than the denominators. So S is sometimes called a scale factor, although in this case, because S is less than 1, we're really talking about scaling down this big triangle to this smaller triangle. If I took the reciprocals of these values, then S would be a number greater than 1. We would be talking about scaling up this small triangle to get the big triangle. If I was taking the ratios big M over little m, big H over little h, big N over little n. That's not what I did here, but it doesn't matter which way you do it. So let's put little m over big M equal to S. And let's put little n over big N equal to S, and just rearrange both of these. Multiply both sides of this by big M. So we see that little m equals big M times S. And from this one here we see that little n equals big N times S. So we know that the tan of angle A from the small triangle is little m over little n, opposite over adjacent. But of course we can now replace little m with big M times S. So we're scaling down this big M by the factor S, whatever it is, some number less than 1 in this case. And since little n is big N scaled down by the factor S, we can divide this by big N times S. Notice that the S's cancel. So we've shown that little m over little n equals big M over big N. So the tan of A doesn't depend on the size of the triangle, of the right angle triangle containing A. In a similar way, we can prove that little n over little h equals big N over big H. So little h is just big H scaled down by the factor S, and little n is just big N scaled down by the factor S, big N times S. S again is some number less than 1, so n times a number less than 1 will give us a number that's smaller than big N, namely little n. Okay, we want n divided by h. Well, for little n we can write ns, for little h we can write big H times S, and you can see the S's cancel. So now we've proven that this result holds. So cos of A is the same no matter which of these two triangles we use, or any size triangle with angle A in it. Finally, if we look at these two ratios here, they're both equal to S. So rearranging this one, we get little m equals big M times S, just the same way, same kind of thing as before. Little h is big H times S. So if we want little m over little h, which is sine of A, we can put big M times S over big H times S. The S's cancel, and we've proven that sine of A is independent of the size of right angle triangle containing A.